Hello Math 2200, Discrete Mathematics. This is Professor Wenson here again to go over the ZyBooks Section 1.6 titled Predicates and Quantifiers. Alright, so Predicates and Quantifiers is Section 1.6. So I'll read this first paragraph here for you. Many mathematical statements contain variables. Right? The statement x is an odd number is not a proposition because its truth value depends on the value of the variable x. Remember, a proposition can be either true or false, but it has a truth value. X is an odd number has no truth value until you replace x with something. All right. So for instance, if x was 5, then the statement would be, 5 is an odd number, which would be true. If x is 4, then you'd have the statement 4 is an odd number, which would be false. So the statement, it's a variable in the statement. See how the truth value varies with the different values of the variable. The truth value of the statement can be expressed as a function p of the variable x, as in p of x. The expression p of x is read p of x. Okay. A logical statement whose truth value is a function of one or more variables, or a statement whose truth value depends on one or more variables, is called a predicate. All right. And they're written in function notation like this: p of x, q of xy, r of xyz here. So if p of x is defined to be the statement x is an odd number, then p of 5 corresponds to the statement 5 is an odd number, right? Just like for functions back in algebra. I replace the variable in the statement with the number 5 and then assess its truth value. Is it true or false? A predicate can depend on more than one variable, right? So here, q is a predicate that depends on x and y, and is the statement x squared is equal to y. So remember, the truth value of this statement, x squared equals y, depends on the value of x and the value of y. Statement r of xyz, x plus y equals z, that statement depends on 3 variables. It is a predicate with 3 variables. Once I replace the variables with numbers, when you replace the variables with values, then you can determine truth value. Then you have a proposition. So you see here, proposition q of 5 comma 25. That means go to q, replace x with 5 and y with 25. Then you'd have the statement 5 squared equals 25, which is a true statement. See, it's true because 5 squared equals 25. The proposition r of 2, 3, 6, replace x with 2, y with 3, z with 6. You have the statement 2 plus 3 equals 6. That is false. Right? So if you have a statement that depends on variables and you don't know the truth value unless you plug numbers in, that's called a predicate. Once you plug numbers in, you can then determine the truth value, so that then you'll have a proposition, right? Something that is true or false. Another key word here: the domain of a variable in a predicate is the set of all possible values for the variable. All right, for example, a natural domain for the variable x in the predicate x is an odd number would be the set of all integers. Now I'm going to be assuming here that you know what the sets of numbers are, like what are the whole numbers, the natural numbers, the integers, the rational numbers, the irrational numbers, the real numbers, the complex numbers. I'm assuming here you know what all those are. All right, and those words will come up throughout the course, and I may re-explain them along the way, but I'm assuming right now you know what those are from previous math classes you've taken. If the domain of a variable in a predicate is not clear from context, the domain should be given as part of the definition of the predicate. All right, so usually a domain will be given. You will be told, in most cases, what the variables represent. All right, so for example, the domain for all the variables in the following predicates is the set of positive integers. All right. So I'm going to write this out, and well, no, I don't need to write anything out. Now the set of positive integers, that's 1, 2, 3, 4, 5, and so on. That's it. Right, those are the positive integers. All right. So whenever you see a variable x, y, or z, it's supposed to represent some positive integer. It can be only replaced by positive integers. All right. So the predicate p of x is the statement x is a prime number. The predicate L of xy is the statement x is less than y. And the predicate S of xyz is the statement x squared plus y squared equals z squared. Now, again, none of these right now are propositions. You don't know if they're true or false. They depend on variables. They become propositions, when you plug when you plug values in for the variables. So is p of 7 true or false? So I go to predicate p and replace the variable x with the number 7. So that would be the statement 7 is a prime number. Remember, to be prime, your only divisors are 1 and itself, and that 7 is prime. So p of 7 is true. I'll do all of these. This isn't that bad. Is L of 6, 6 true or false? So I'll go to statement L, replace x with 6, y with 6, giving me the statement 6 is less than 6. Is 6 less than 6? No, it is not. 6 is equal to 6, not less than 6. So the statement L of 6, 6 is false. Is S of 3, 4, 5 true or false? So I go to S, predicate S here, replace x with 3, y with 4, z with 5. Pay attention to the order. And that gives me the statement 3 squared plus 4 squared equals 5 squared. Right, is that true? Is 3 squared plus 4 squared equal to 5 squared? And yes, 9 plus 16 is equal to 25. So S of 3, 4, 5 is a true statement. Okay. So it's just like functions, but with statements, whole statements, instead of algebraic functions like you're used to. All right, and you can read the other example here. All right, let's go into this. Which sentences are propositions and which are predicates? The domain is, again, pay attention to the domain. Right? Look for this word. Right? Pay attention to the domain of these predicates. What numbers, what types of objects can I replace the variables with? And here again, the domain is the set of all positive integers. So just 1, 2, 3, 4, 5. Not 0, not -1, right? Just 1, 2, 3, 4, 5, and so on. All right. X is odd. Is this true or false? I don't know. And because I don't know if it's true or false, right, because it depends on a variable, this is a predicate. 23 is a prime number. There's no variable in here. And this is a true statement. Right? It's something that is true or false. So this is a proposition. And these two have variables, right? So they're predicates. Just fill that in. That depends on a variable. The truth of this statement depends on the variable x. Okay. All right. Now we're going to get into what are called quantified statements. Okay. And again, I'll do some reading. This is important, the beginnings of these headings. If all the variables in a predicate are assigned as specific values from their domains, then the predicate becomes a proposition, as we've seen, with a well-defined truth value. Another way to turn a predicate into a proposition is to use what's called a quantifier. Right? The logical statement. Now, this upside down A means for all. For all. Right? So for all x, or for every x, for all x in the domain P of x, meaning for every value in the domain, the predicate is it will be a true statement. That's what this means. So we had for all x, P of x, or for every x, P of x. So this statement, for all x, P of x, asserts that P of x is true for every possible value of x in its domain. That upside down A symbol, right, is called a universal, right, universal quantifier. Right, the universe, everything in the domain will make this statement true. And the statement for all x, P of x, is called a universally quantified statement. Right. For all x, P of x is a proposition because it is either true or it is false. For all x, P of x is true if and only if P of n is true for every n in the domain of variable x, right? Like I was saying earlier. Right. This is only a true statement if for every value in the domain, the predicate will be a true statement. So another way to write this, suppose the domain is a set of elements from A1, A2, all the way up to AK, then saying that for every x, P of x is logically equivalent to saying that, P is true when I plug in A1, and when I plug in A2, and when I plug in A3, and when I plug in the last value in the domain. All right, so saying for every x, P of x, pardon me, is the same as saying the predicate is going to be a true statement. It will be a true proposition when I plug in any value of the domain. Right. So the equivalent symbol means that two expressions always have the same truth value. You've seen it before. If the domain is that's an example. Right. So to prove that a statement like this is true, establishing that for all x, P of x, or for all x, A of x is true requires showing that every value in the domain makes the statement true. So if the domain is finite, if the domain is only k, 5 elements large or 10 elements large, that's easy. You just plug in every single value. But if the domain is infinite, like the set of all real numbers or all positive integers, then you're going to have to prove the statement for any general value in the domain. Call it x or something. And in a proof like that, and we'll do a lot more proof writing in chapter 2. But when you're proving a universal statement, if you want to prove it true, you start off with some statement that is known to be true, and then you work your way from there until you show that the statement is true in general, right, for any value of the domain. Now to prove, well, we'll get to that later. To prove, I'll come back to the problem. A counterexample for a universally quantified statement is an element in the domain for which the predicate is false. So if you want to prove that a universally quantified statement is false, you just need to find one value in the domain that makes the statement false, that makes the predicate false. Because it says for every x, P of x. Well, if you can find one x such that P of x is not true, that's called a counterexample, and it shows that the statement is false. Alright, so let me show you what they're doing here. Alright, I'll write it on some paper. So we have this universally quantified statement. Now, we're told here that the domain is, again, just the positive integers, right? So anytime I see a variable, it represents some positive integer. All right, and that's this set again, 1, 2, 3, and so on. All right. Now we're trying to, if you watch the animation, which I'm going to write out by hand here, show you what's going on. They're trying to prove the following universally quantified statement. Prove that for every single x, then here's p of x. 1 divided by x plus 1 will be less than 1, the number 1. Right. So this is, if I write this in words, for all, x is a positive integer. So for all positive integers, say, represented by x, then this statement here is the p of x, the predicate. Right. 1 divided by x plus 1 will be less than 1. Right. So here, the domain is infinite. Right. There are infinitely many positive integers. So I can't just do a couple examples, if x were equal to 1, for the integer 1 divided by 1 plus 1, that's a half, which is definitely less than 1. Replace x with 2. 1 divided by 2 plus 1 is 1/3, which is definitely less than 1. Replace x with 3. 1 divided by 3 plus 1 is 1/4, which is definitely less than 1. That's not a proof. All right. I'll write that right now, and you're going to see again in chapter 2. Chapter 2 is all about proof writing, but we're going to see that several examples do not prove a universally quantified statement. And that's big. All right. Just because I showed you that it works for 1, 2, and 3, that doesn't mean it's going to work for every positive integer, right? There are infinitely many other examples I could think of. So, I mean, what if it didn't work for a billion? You wouldn't see that for a while. So just show, when you have a universal statement with this upside down A for all, for every, just showing a few examples of how it works, of it working, right? Oh, here's 3 examples of this working. That does not show that it's true. Right? You have to show for every. Now, when the domain is infinite like this, you're going to have to start off with some, to prove it, you're going to have to start off with some statement that you know is true about a positive integer called x, right? And we're going to use a letter and not a specific example. Like here I replaced x with 1, here I replaced x with 2, here I replaced x with 3, but I don't want to replace x with a specific number. I'm going to use just some generic x. X represents some positive integer. Now if x is a positive integer, we know this much. X is positive, right? X is greater than 0 for sure. You start with something you know, right? Start with a true statement about your object, right? About our number here, our positive integer called x. If x is a positive integer, I know it's going to be greater than 0 because it's in the word, it's in the name, it's a positive number. And then I work through using manipulations like using rules, equivalence and inequality rules from algebra that you know to be true. You just keep using things that you know are true, that have been shown to be true to you, until you get to the statement in question. So I'm noticing this plus 1 being, what if I want to make this so that there's a plus 1 by the x? So, law of inequality, I can add 1 to both sides, and that wouldn't change the inequality, right? So then, following from this, x plus 1 must be greater than 1, right? That should be true. If x is greater than 0, just adding 1 to both sides. And if x is greater than 0, x plus 1 is greater than 1. So x plus 1 is definitely positive, right? Because it's greater than 1. That means I can divide both sides by it, and it won't change the inequality. Remember, when you divide both sides by a positive number, so I'll divide by x plus 1 over here, divide by x plus 1 over here, and that gives me the 1 over x plus 1 that I'm looking for on the right side here. And this is dividing by a positive number, right? X plus 1 is positive. So the inequality will not change. Remember your algebra rules. And so now I have on the left side, right, anything divided by itself is 1. I have 1 is greater than, 1 divided by x plus 1, which is the same as that statement there, right? Just switch the sides. Just switch them. 1 over x plus 1 is less than 1. And we're done with the proof. I have shown you that if I take, and this is really not just for positive integers, but for any positive number. I've just shown you that if I take a positive number called x, any positive number called x, it's going to be the truth that 1 over x plus 1 will be less than 1. So there, I've just shown you, starting with a true statement and then keep building on that with things you know to be true, rules that you've learned from algebra or whatever other class you've taken before, some basic stuff to show the statement that's in question. That this is how you prove a universally quantified statement. Right, you start with a generic statement, something true about your domain values, right? Our domain values are positive integers, so they're greater than 0, and then you go from there using more and more true statements, building upon itself until you show that this statement after the quantifier must be true. All right. So again, we're going to do this a lot more. Right? If this didn't make a lot of sense here, hopefully it will. When we go in chapter 2, we're going to be doing a lot of proof writing. All right. So that's how you would show, and that's what they're doing here in the animation, right? To show you that a universally quantified statement is true if you're asked to prove it. Like I said, counterexamples. Counterexamples, they show that a universal statement is false. Right? To show that a universal statement is false, you just need to find, I've said this already, you just need to find one value in the domain that makes the statement in the predicate false. All right, so look at here. So in the following questions, the domain is this, again, now this will change sometimes, but so far the domain has been the set of all positive integers. Just careful when you read. Indicate whether the universally quantified statement is true or false. All right, so I'm going to start with this. I'll do this first one on paper. All right. So again, the domain is positive, all the positive integers. Right. So anytime I see a variable, it's representing some positive integer. But now, the statement is this: for all x. So this means for every positive integer, which I'll call x, the following statement: x squared is greater than 0. Now let's see. Now you can prove this is true pretty easily, but I can start off with some examples, right? Just to believe it. Right? And again, we'll do this in chapter 2 as well. But I start off with some examples, right? So there are infinitely many. Let's just start with the first few. Replace x with 1. We have 1 squared is greater than 0. That's true. I'll put a t. 1 is greater than 0, right? Replace x with 2. 2 squared, is that greater than 0? Yeah. 4 is greater than 0. 3 squared is greater than 0. Yeah. 9 is greater than 0. Again, this is not a proof. All right? This is not a proof. These are just examples. Proof. These are just examples to see if I believe it, because who knows? Maybe there's a number 500,000 down that makes it false. I don't know. But just showing a few examples doesn't show a universal statement to be true. But I know again that x, right? Again, if this is the values in my domain are positive integers. So I'll start with, again, x must be greater than 0. I'll start with something I know. And then since x is a positive number, right, it's a positive integer, multiplying both sides by x won't change the inequality, right? Since again, x is positive, right? X is some positive integer. And that gives me x squared on the right is greater than any number times 0 is 0. And oh look, that's the statement. This is true. This is a true statement for any positive integer. All right, so that's true. All right, now I'll do one more. All right, so again, the same thing. The domain, what every variable represents, is some positive integer. The next statement in that activity was this. It says for any x, right, for all positive integers, you take any positive integer and subtract 1, it's going to be, the result is going to be greater than or equal to 0. All right, and let's try it out. Examples. And let's just start with 1 here. All right, replace x with 1. Is 1 minus 1 greater than or equal to 0? Well, you got 0 is greater than or equal to 0. Yeah, it's equal to 0. Right? And then replace x with 2. Is 2 minus 1 greater than or equal to 0? Yeah. Right, that's 1 is greater than or equal to 0. That's true as well. Again, not a proof. Just because I show a couple examples, it's not a proof. We have to show for all, and there are infinitely many. There's no way you're going to write out infinitely many examples. But this, just after a couple, I'm believing it. Right? I'm believing that this is a true statement. So again, I start with something I know. Right? X is a positive integer, so I know that x is greater than 0 for sure. Right? X is greater than 0 for sure. In fact, since I know x is a positive integer, I can start even a little higher. This includes greater than or equal to. I want greater than or equal to involved. In fact, instead of using x is greater than 0, since x is a positive integer, 1, 2, 3, 4, I know x is going to be greater than or equal to 1. Right? It's 1 or greater. That's what this means. So any positive integer is going to be greater than or equal to 1. And then subtracting 1 from both sides, I get that statement, right? Minus 1, minus 1. So any positive integer minus 1 will be greater than or equal to 0. Yes, that is, so it is true. All right, so that's true. Now what about this last one? What about this last one? All right. So again, the domain is all positive integers. All right, the domain is positive integers. And the statement is, for any positive integer, x minus 1 is greater than 0, just greater than 0. All right. So for all x, for any positive integer x minus 1 is greater than 0. Let's see. Let's try some examples. Again, starting with 1, pretty easy here. Is 1 minus 1 greater than 0? That's 0 is greater than 0. No, that's false. So they would say that x equals 1, right? When I replace x equals 1, is a counter example. It shows that this universal statement is false. All right. Now for the rest of them it's true. For 2 it's true, 3 it's true, 4 it's true, 5 it's true, but for 1 it is false, right? And this says for every positive integer this statement should be true. Every. So including 1, but it's not true for 1. Right? So one would be any of the, you find an example that makes it false, a universal statement false, that's called a counter example. All right, so this statement then is a false statement. All right, just with a simple, you just got rid of that or equal to part. Okay. All right. Now that was a bunch of examples of for every, right? For every value in the domain, this is true. Right. The next type of quantifier is there is or there exists. There is at least one. So the existential quantifier, right? Those were universal quantifiers. the logical statement, this is there exists an x such that p of x is true. So to prove a statement like this, to prove that this is true, you just need to find one. Find one value in the domain that makes the predicate true. That's it. And to show something like this is false, you have to show that there isn't any value in the domain that makes this true. All right, so you have to show that every value in the domain would make this p of x false. Right. So the logical statement, it's a backwards E symbol for there exists. There exists x such that p of x. There exists an x such that p of x. The statement there exists an x such that p of x asserts that p of x is true for at least one possible value of x in its domain, right? You just need to find one. There may be more, right? There might be more values that make it true, but all you need to do to prove that this statement is true is find one. This backwards E symbol is called an existential quantifier, right? There exists. And this statement, there exists an x such that p of x, is called an existentially quantified statement. Right. And if you have only so many, if you have a finite number of values in your domain, say again a1 through ak, there is an x such that p of x is equivalent to saying that p could be true at a1, or p could be true at a2, or a3, or a bunch of ors, or at ak. And remember, this is the inclusive or, so p could be true for at least one of these a1 through ak. P is true for at least one value in the domain. All right. So first little activity here they have is showing that an existentially quantified statement is false. All right, and I'll go through this on paper as well. So again, the domain is positive integers. I'll just keep that up top. And we're given this statement. There exists, there is an x. There is a positive integer, at least one, such that x plus 1 is less than x. Right. So again, in words, this little symbol, this tells me this is saying there is at least one positive integer. There exists, or there is at least one, the domain is positive integers. And just, again, pay attention to the domain. It might be something else, not the positive integers. There is at least one positive integer, say, called x, such that this statement is true. And this is the predicate p of x, the statement that depends on a variable. All right. Now, I said earlier, to show a statement that's existentially quantified is true, you just need to find one value of the domain that makes the statement true. To show that an existentially quantified statement is false, you must show that, not p of x. You must show that, not p of x is true for all x, right? Or show this statement for all x, not p of x. Right. In other words, show that this is false no matter what you plug in. All right. Now again, you can go through some examples. When x is 1, you got 1 plus 1 is less than 1. That's 2 is less than 1. That's false. But remember, that doesn't mean this statement is false. That doesn't mean this statement is false. Just showing it's false for 1 doesn't mean that this existential statement is false, because all you have to find to show that it's true is just find one number that would make it true. So who knows? When I plug in 2, you get 2 plus 1 is less than 2. That's 3 is less than 2. That's false. I could keep going. What if when I plug in 1 billion, it works? Then this would be a true statement, because the only thing that in order for this to be true, you only need to find one number that makes it true. So showing that a couple examples make it false doesn't mean it's false. We have to go in general. Now what I'm going to do this time, all right, and again, we'll see more of this in chapter 2. To prove that an existentially quantified statement is false, instead of starting with something that's true, we're going to assume the statement is true first. And then, hopefully through some use of other true things, other laws we've learned, algebra rules and stuff, we end up with something called a contradiction. If you remember, a contradiction is something that's always false. Right. And if you do that, if you end up with a contradiction, then that means your assumption must have been wrong. So I assume the statement is true. So there is an x. I don't know what it is. There is a positive integer x. Such that x plus 1 is less than x. All right. So I start off assuming that the statement is true, that I can find an integer x, and then we'll see what happens. All right. If there is one like this, if there is a positive integer x such that x plus 1 is less than x, if I just simply subtract that x from both sides, look what we get. You get the statement 1 is less than 0. This is a contradiction, something that is always a false statement. So that means that this assumption must be wrong. So assuming the statement was true led me to a false statement. So that means this statement must be false. Okay. It's called a proof by contradiction. We'll see a lot more of those in chapter 2. I wouldn't worry about it so much right now. You're just asked to kind of say if things are true or false without really proving them right now. But that's what they're getting at here in the animation. All right. So let's get to let's say some of these out loud here. All right. So in the following questions, the domain is again the set of all positive integers. All right. I don't know why it's always the set of positive integers in this book, but in some of the exercises, you'll see the domain changes. Well, yeah. See here in the additional exercises, the domain is just the set of all integers, so not just the positive ones. So be careful. Just pay attention. Read carefully. All right, so indicate whether the existentially quantified statement is true or false. So there is a positive integer whose square is negative. That's false, right? 1 squared is less than 1 squared is positive, 2 squared is positive, 3 squared is positive, and so on, right? And if you assume this was true, if x squared were less than 0, then you can very easily kind of show that that's not so, right? Because any real number squared is going to be positive, right? Except for 0. So this is false, right? There isn't a positive integer whose square is negative, right? There exists a positive integer such that that integer minus 1 is greater than 0. Sure. 5. 5 minus 1 is greater than 0. There, I found one. It's true. Again, there's more, sure. 100 minus 1 is greater than 0. 1,000 minus 1 is greater than 0. But as long as you can find one, as long as you can find one, a value that exists in the domain that makes the statement true, then that statement is true. Does that make sense? I don't know why I'm asking that. You can't answer me. And then there exists an x. There is a positive integer whose square is equal to itself. Well, yeah, sure. 1. 1 squared is 1. So this is true as well, right? Again, to show that there exist statements, these existentially quantified statements are true, you just need to find one example, one value from the domain that makes the statement true. And if you can't find one, either you're not looking hard enough or it's probably false, and then you'd have to, again, in chapter 2 we'll go over proof. I did some proofs here, but not too many, and we'll go over more proof writing methods in chapter 2. All right, and all right. So again, I want to go through this. These are important. How do you show that a universal statement is true? You have to show that for every element in the domain, the statement is true. All right. So to show that a universal statement is true, you have to show that for every element in the domain, the statement is true. How do you show that a universal statement is false? You only need to find one element in the domain that makes it false. All right, so give a counter example, right? A particular element in the domain for which the predicate is false. That's this fourth statement. How do you show that an existential statement is true? You just need to find one value in the domain that makes the statement true. Give a particular element in the domain for which the predicate is true. That's the first statement there. And finally, how do you show that an existential statement is false? You have to show that there is no value in the domain that makes this true, meaning every value in the domain makes it false, right? Show that every value in the domain makes the predicate a false statement when you plug it in. Okay. And then you have additional exercises, which again show up in your assignment. I didn't assign all of them. You can see the solutions here to any of them if you wish, right? Please work on them first. Try to learn how to do them. Figure it out on your own before you look at the solution. Don't just write the solution. You're not going to learn anything, and that's just going to hurt you in the long run when I give you exams. And also, I didn't assign every problem in the additional exercises. So if you want some extra practice, I recommend actually doing all the additional exercises. So you can get more familiar with the material. And of course, if you have questions, let me know. And I hope this was informative for you and learned about predicates and quantifiers. And that's it for section 1.6. Thank you very much for watching.